Hi, welcome to the Chalk&Talk summary of the first week. Here in this whiteboard, I will try to explain why I explain it in the PowerPoint videos, but this time writing by myself the transition states and everything, and I hope that you can do it at home the same way that I am doing here. That means it's important that you draw the transition state by yourself, not only base your knowledge in what I do in the PowerPoint. Okay? Okay, the first part of the course, of the lecture, was about proline. Remember, proline is a 5-member ring. With a nitrogen, a pyrrolidine, plus a carboxylic acid. It's a bifunctional catalyst. Okay? Why? Because we have a carboxylic acid plus a secondary amine. The secondary amine is basically to form enamine, and as I explained it, the carboxylic acid is working in order to activate and direct the electrophile. Okay? This is basically what is doing the proline. The two functional groups of the proline, both are very important. Okay? And now what I will do is how we can build the enamine. I will not put all the mechanisms how we get the enamine, because this is in the PowerPoint, it's in the PowerPoints, in the video PowerPoints, or in the PowerPoint. Also, it's something that you need to know from last year courses. Okay, that means we have here a ketone, okay, and we add the proline. Okay? Okay, remember, this is forming the enamine. Okay, what is important here? The important thing is that the carboxylic acid and the enamine, the double bond of the enamine, are on opposite sides of the enamine. Okay, carboxylic acid in this case to the right, the enamine to the left. This is in order to avoid a steric interaction between this hydrogen here in this position and the carboxylic acid. Okay? Second thing that we have to be aware is this R group always pointing down. Why? In order to avoid the steric interaction between this R group and these two hydrogens of the pyrrolidine. Okay? This is the correct conformation, the correct configuration of the enamine. Okay? Always that we are using an enamine, we have to draw the correct enamine. That means carboxylic acid in one side, double bond in the other side, and the R group always pointing down. Okay? Good. Then, once we have cleared this, we can use this enamine in order to do reactions. Okay? We will start with the aldol reaction. Okay? The aldol reaction basically is a ketone plus an aldehyde. In this case I use a non-enolizable aldehyde. That means that whatever I do, I add here the catalyst, I cannot create an enol, I cannot create an enamine because I don't have any alpha proton to the carbonyl group. and I add proline. Okay, then first step, we form the enamine as I did before. Okay, double bond of the enamine and the carboxylic acid, each one in one side of the enamine, and this group pointing down. Check that in this case, I only can have one enamine. If I do the enamine on the other side, it will be exactly the same. Okay, then this is reacting with aldehyde. How is approaching the aldehyde? Remember that enamine is a bifunctional catalyst. This is the nucleophile, this will act as a nucleophile, the enamine, but the carboxylic acid has two functions. One is to activate the electrophile by hydrogen bonding, and to direct, by the same hydrogen bonding, the attack of the nucleophile. Okay, this is the carboxylic acid. And then the first step is the coordination of the aldehyde with the proton of the acid activating it. Now, this carbon is by far more electrophile. Okay, then, there are two possibilities. I can put here this approach of the aldehyde with the phenyl far away of the carboxylic acid, or just the opposite with the phenyl close to the carboxylic acid. Which do you think that will be the most stable? Well, basically, will be the more stable when more far away is the phenyl to the carboxylic acid. We always will have the approach of the aldehyde with a big group, in this case the phenyl, far away. Okay? Well, then, what is happening now? Well, now we have everything, and then the enamine will attack. The aldehyde, as you can see here, and because the carboxylic acid is in front of the whiteboard, the approach of the aldehyde must be in front of the whiteboard. Okay? That means if we do this, what we will get is what we will get is this final product. Okay? I don't recommend to draw this. You can draw directly the hydrolysis. That means that the final product will be this. Right? Okay? Remember, the carboxylic acid of the proline is activating the aldehyde and directing the attack. That means, in order to have this coordination, the approach of the aldehyde has to be in front of the whiteboard, because this is going in front of the whiteboard, and then the nucleophile, the enamine, will attack to form, if you translate well the stereochemical information, to this final product. Okay? Good. Okay, this is related to the aldol reaction, but what happens if instead of aldol, what we do? Is a Mann's reaction between a ketone and an imine. Well, the first step is always the same. We need to form the enamine, and we follow exactly the same rules that we had before. It means double bond and carboxylic acid, one far away of the other, and the R group, this group, pointing down. Okay, remember that this is to avoid aesthetic interactions. And then, again, like before, we know that the proline is a bifunctional catalyst. That means we know that the carboxylic acid is coordinating with the imine okay? And now the main difference is that when we have this imine, the only possible coordination of the hydrogen with the nitrogen is by this pair of electrons, isn't it? That means that the coordination has to be opposite to this phenyl. And because all of the major part of the imines are Z, that means the phenyl, the two big groups are in different sides of the imine, okay, this time the big group is close to the carboxylic acid. Okay, now what we want to do is we form this nitrogen-hydrogen bonding, okay, and in order to do this, the only pair of electrons of the nitrogen is opposite to the phenyl. In the case of the aldehyde, remember that we have two pairs. We can coordinate by this phase, by this side, or by this side. In the case of imines, we only have one pair of electrons that can be coordinated with the carboxylic acid, and for this we have this approach of the imine. Okay? And the approach of the imine will be, as before, in front of the slide. Why? Because this carboxylic acid is in front of the slide. Then what will happen is that we have the attack of the enamine to the imine, and what we get, and this time I will do that, we get the final product okay. We will get this final marriage product. Okay? What is important? Is the approach of the imine. The only difference with the aldehyde is that now we can only use this pair of electrons. That means that the phenyl group in the carbon will be faced to the carboxylic acid in this case. Okay? Good. This basically is the most important about the proline catalysis. Okay? Always work the same. That means we have an enamine, we have a carboxylic acid. The carboxylic acid coordinates with the electrophile by hydrogen bonding and direct and activate the attacks of the enamine. What happens happens if we are using the Jorgensen-Hayashi catalyst. Okay? The Jorgensen-Hayashi catalyst is slightly different than okay, it's slightly different and it's not a bifunctional catalyst. We only have a functional group that will work. This is the secondary amine that is working to form the enamine. While all these things are basically a shield. Will shield one phase of the enamine. Again, the most important is to know what is the configuration of the enamine. In this case, remember that all this catalyst normally only works with aldehydes. If we form the enamine, we follow exactly the same rules than before. Double bond of the enamine and the bulky group, in this case this diphenyl OTBS, in different sides of the enamine, and this group always pointing down. The reasons, like before, to avoid interaction between this hydrogen and this, or to avoid spherical interaction between this R and these two hydrogens. Okay? But now what is the difference when we are doing a reaction? The electrophile, here is the electrophile, okay, can come from two directions. If we put the enamine in the plane of the whiteboard, the electrophile can come from in front or from behind. What happens if the electrophile comes from in front of the light? Well, the electrophile will go and will crash with this group. This group is going out of the screen, going in front of the screen. That means the electrophile will crash with this, will not approach to the enamine, will not work. The electrophile in this case has to come from behind. That means that the electrophile, the approach of the electrophile will be from behind, and the attack of the enamine, and what we will get this final product. Okay? Check that if the electrophile is approaching from behind the slide, this will be the final configuration. Okay, what's the difference between this catalyst and the proline catalyst? The only difference is that in proline catalyst, the carboxylic acid that we have in this position is directing the attack. The electrophile approach will be for the same phase where we have the carboxylic acid. In the case of the Jorgensen-Hayashi catalyst, this group is only shielding. That means that the approach of the electrophile will come from behind the enamine, behind the whiteboard. Okay? Finally, we talk about the Macmillan catalysts that are exactly the same in this. The only difference of the Macmillan catalyst is that are structurally little bit different. Okay, we have the first this is the first generation. This is the second generation. and this is the third generation. Okay? All three works the same. The only that we have to consider in order to form the enamine is which is the bigger group. The bigger group will be the dimethyl, will be the terbutyl, and will be the terbutyl. That means when we are forming the enamine, we follow the same rules than before. This catalyst also only works with aldehydes. Okay? If I want to form the enamine, double bond of the enamine far away of the big group. Remember that the big group is the dimethyl, not the benzyl. Okay, because the dimethyl is occupying all the space, the benzyl only occupies the space behind the whiteboard. Okay, and in this case, this group is shielding the face behind of the whiteboard. That means if the electrophile will come from in front, the approach will be from in front. That means that we will get what we will get is this final product. Okay, in the second case, exactly the same. We form the enamine. Okay, and again, like before, the big group, in this case, the terbutyl opposite to the double bond of the enamine in opposite sides, and this group pointing down. And again, in this case, this group, the terbutyl and the benzyl, both are blocking the face behind the whiteboard. That means that the electrophile will come from in front, will come from here, the electrophile, the enamine will attack the electrophile, and what we will get is this final product. Okay? In the third case, it's the easier case, the third generation of Macmillan catalyst. We form the enamine following exactly the same rules that we did before. Okay? Again, big group, the terbutyl opposite to the double bond of the enamine, and this group pointing down. And the electrophile again, the terbutyl is blocking the face behind the whiteboard. That means that the electrophile will come from in front. And what we will get is this final product. Okay? This is a very fast summary of the first lesson, the enamine lesson, that is basically the first week. Of this course. Okay? Please try to grow everything at home. Try to understand why I grow the configuration in the enamines that I grow. Do the exercise and